In the previous video, we were working on formalizing the notation that we use for a Riemann sum, and we came up with this kind of stuff. Basically, a Riemann sum for a particular definite integral is any summation of the form Sn is equal to f of c1 times delta x plus f of c2 times delta x plus and so on until we get to plus f of ck times delta x, and we keep going until we finally reach plus f of cn times delta x, where the delta x is equal to b minus a divided by n, that is the width of all of the rectangles, and the ck's are sample points from the kth subinterval, and the kth subinterval is either written as xk minus 1 to xk, or it can be written as a plus k minus 1 times delta x to a plus k times delta x. So these two statements are saying the same thing. And this is all where we're thinking about x0, x1, dot, 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 down to xn is a partition of the interval between a and b. And in fact, what we're thinking about here is an equal width partition, and this x0 is equal to a, and this xn is equal to b. Now, this is really awkward notation. It is long to write, and it is awkward to say or read. We need better notation for writing that sum. So what I want to do is I want to introduce something called sigma notation. Now, this symbol that looks kind of like a capital M on its side is the Greek letter sigma, and it is a capital sigma. A lowercase sigma looks like that, so that is a little lowercase sigma. We're not going to use any sigmas in this class, but if you take a probability and stats class, sigma plays an important role in probability and statistics. But capital sigma is used to denote summations because sum begins with a capital S or a sigma. Now, the way we use the sigma notation is we have a counter, which we will call k, and we have to have a starting value, and we have to have an ending value, and we have to have some kind of a term, which is usually a function of k, but not always. So as a basic example, and I should say that k is called the counter variable. And as a basic example, let's look at the sum as k goes from 1 to 5 of 1 over k. Well, when k is 1, I get 1 over 1. When k is 2, I get 1 over 2. When k is 3, I get 1 over 3. When k is 4, I get 1 over 4. And when k is 5, I get 1 over 5. And because 5 is equal to my ending value, I stop. The sigma says to put in the plus signs. So this notation is usually read, and I want to kind of think about how to read it. This notation here is usually read as the sum, that's the sigma, as k goes from 1 to 5 of 1 over k, and it winds up translating into this sum. K is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, k is equal to 5. Now, there are a couple of things about this summation notation that I want to note right now. The first one is we're going to look at sigma notation in much more detail later in the course. Right now, what we want is to learn just enough about sigma notation to handle Riemann sums. So one thing that we want to do is I want to note that the starting and end value of a summation are very important. And I'm going to do that with just a basic kind of an example. I'm going to look at the sum as k goes from 2 to 6 of 1 over k. We have the same term, but our start and ending values are different. This one is going to start with 1 over 2, and then we have 1 over 3, and 1 over 4, and 1 over 5, and we stop after we get 1 over 6. And because this sum and this sum are not the same thing, I want to immediately note that the summation as k goes from 1 to 5 of 1 over k is not the same thing as the summation as k goes from 2 to 6 of 1 over k, even though they both have 5 terms. The next thing that I want to look at in sigma notation is the fact that the counter variable inside sigma notation is a dummy variable. And let me correct my handwriting there. This is a dummy variable. Just like the variable in a definite integral is a dummy variable. If I have the sum as k goes from 1 to n of ak, that's going to be a1 plus a2 plus a3, and we keep going until we get down to an, whatever the a's are. On the other hand, if I write this sum as the sum as I goes from 1 to n of ai, this is also going to be a1 plus a2 plus a3 plus all the way down to an. In the top summation, what we are doing is we're saying k is equal to 1, k is equal to 2, k is equal to 3, k is equal to n, and we have the plus signs. In the bottom sum, we're saying I is equal to 1, I is equal to 2, I is equal to 3, I is equal to n. But the expression that we get is clearly the same thing. These two expressions are equal, and consequently, the summation as k goes from 1 to n of ak is going to be the same as the summation as I goes from 1 to n of ai. In other words, the variable that we use to describe the term doesn't matter as long as the starting and ending values of the summation are the same. Now what I want to do is I want to actually relook at our Riemann sums. So I want to recall that Sn is equal to this particular expression. And the only things that are changing in that expression are the subscripts on the sample points. In other words, each term has a sample point plugged into the function, and then we multiply by delta x. And as a consequence, we can rewrite this long expression as Sn is equal to the sum as k goes from 1 to n of f of our sample point for the kth subinterval times delta x. Now, the authors in our book have a tendency to write this sum as the sum as I goes from 1 to n of f of ci times delta x, and they're the same thing because the variable of the summation is unimportant. What is important is that we have the same formula, we have the same starting value, we have the same ending value. I prefer k's because my eyes are hard to read sometimes. That's the only reason that I use k's. Now what I want to do is I want to actually think about what this says in terms of the Riemann sum so that we know how to read this in terms of Riemann sums, and I want to state the formal definition of what a Riemann sum is. So the formal definition of Riemann sum can now be written very compactly as, this is a formal definition for a Riemann sum for the integral between a and b of f of x dx. The Riemann sum is going to be called Sn. It's going to be given by the summation as k goes from 1 to n of f of ck times delta x, where, first of all, delta x is going to simply be b minus a divided by n, and informally, it's important to remember that this is the number of rectangles that we are using. It is also the number of subintervals. And back to the formal stuff, our sample point has to lie between x sub k minus 1 and x sub k. And informally, this is simply saying that ck belongs to slice k. And we want to also say something else. xk minus 1 is going to be equal to a plus k minus 1 So a plus k minus 1 times delta x's, and xk is equal to a plus k times delta x. We didn't worry about this in our informal version of the definite integral. So this is the formal definition of a Riemann sum. The very last thing that I want to do is to go from Riemann sums to the formal definition of the definite integral that Riemann came up with. So, the formal definition of what we now call the Riemann integral. And the Riemann integral is indeed denoted as the integral from a to b of f of x dx. And Riemann defined this particular set of symbols, which we do know to be the signed area, trapped under the curve y is equal to f of x and over the interval between a and b. Riemann's definition says that this thing, the signed area defined by that set of symbols, is going to be the limit as the number of rectangles gets big and their widths go to 0 of the sum as k goes from 1 to not 1 to infinity, from 1 to n. Sorry about that. Of f of ck times delta x. Now it's important to understand that what this particular set of symbols is saying is that the definite integral is the limit as n goes to infinity of delta, and as delta x goes to 0, of the sum as k goes from 1 to n. And now I'm going to go into the informal stuff. This is the height of the kth rectangle. That is the width of the kth rectangle. So we are looking at area of rectangle K. And so what we really do have is that the formal definition of the Riemann integral is we're simply going to let the number of rectangles zoom off to infinity, and we're going to let the widths of the rectangles drop down to 0. And the limiting value of the Riemann sums is the area under the curve. We will explore this idea in more detail in the problem solving next week and in future videos.